Welcome everyone to today's CDAC webinar. It's my great honor and pleasure to introduce today's speaker, Professor Patrick Cordier, who's joining us from Lille, France. Patrick is one of the world leaders in transmission electron microscopy of minerals, and in particular, the study of plastic deformation and defects in minerals using TEM and related techniques, as well as various numerical methods. He's led a very productive lab at the University of Lille for the past 3 decades or so. That's where he also received his master's and PhD degrees. Patrick has many honors, including fellowship in the American Geophysical Union and the Mineralogical Society of America, the award of an MSA Dana Medal, laureate in the Institut Universitaire de France, and elected membership in the Academia Europaea, just to name a few. Patrick and I first started interacting during the 1990s, early 1990s, when there was a great flurry of discoveries in the amorphization of minerals, in particular beginning with quartz, a favorite mineral of ours. So Patrick, it's great to reconnect and to visit mineral amorphization, this time applied to olivine, and this is the first talk on amorphization in this series. So welcome. I'm glad you're able to join us.
Thank you very much. Thank you for this extremely kind introduction. And indeed, I will speak about a subject that I'm happy to meet. But I have to start with a slide as an apology, because in this series, since I'm setting the stage at the lithosphere, well, of course, we will not reach extremely high pressures as you might be used to meet in this seminar series. But still, well, the lithosphere is still interesting. It's a place which is central for many processes, plate fracture, seismic rebound, and also especially the lithosphere, asthenosphere, is not only very interesting from the rheological point of view, which is what I'm interested in, but also it's where, in a simple view, where mantle convection couples at least partially with plate tectonics. So it's really important. And when we try to describe the mechanics of the lithosphere, people used to use this simple descriptions, the kind of Christmas tree, which basically try to say that at some point in the rigid, brittle side, you have the envelope which is following the Byers-Lees law, so it's frictional plasticity, if you like. And then at some point, and depending on the conditions, you meet a different regime where the rock becomes ductile. So of course it depends, and here in this paper from Warren and Hansen, they used the grain size as a parameter. When it's very small, well, you meet earlier the transition to diffusion creep, and when the grain size is coarser, it comes later and it goes to another regime. And they mentioned grain boundary sliding, and I will speak about that. And so this regime here, where we transition from one mechanism to another, is something which is kind of interesting. But well, since we're speaking about the lithospheric mantle, the mineral which is of interest is olivine. Olivine has been studied for many years, but still it's kind of a complicated problem from the ductility point of view. And I will try to tell you why. Of course, there are many evidence that olivine is ductile and carries plastic deformation. To name only one, the development of crystal preferred orientation is a witness of its evolution, and it's used to track fossil strains in the mantle through seismic anisotropy, for instance, but also from the microstructures, from the shape of the grains, and from this contrast, those lines inside the crystal, we have evidence that there is plastic deformation. Of course, we look at that at the TM. This is what we're used to do, and we see dislocation. We see also that the dislocation, they arrange in these subgrain boundaries very straight, and this tells something, which is because the grain is curved, is bent. And this is due to the fact that in this mineral, which is of rhombic, there are not enough slip systems to really achieve a general deformation. First of all, because, well, 0, 1, 0 slip is impossible for crystallographic reasons. So we are left with only 2 slip directions. And even this one, 100, is only active at high temperature. So this is by far not enough. And this is one of the reasons which led the team of Dave Kolschet and Hansen to propose, from the analysis of the mechanical constitutive equations, to propose another mechanism at the grain boundaries, giving another degrees of freedom, grain boundary sliding. It's only very recently, in 2019, that Caroline Bollinger and Bayreuth did prove with microstructural evidence the activation of motion at grain boundaries. So to further study this mechanism, Sylvie de Mouchy, a few years ago, started a project where she was deforming very small, fine-grained olivine polycrystals in the Patterson press. And while the results are presented in this paper, of course, it's not my goal to present that. I will just focus on 3 of those results, because readily you can see that here there is a transition in the rheology at about 1000 degrees C. Below that, the stress is very high and not much ductility is brittle. At 1200 degrees C, it's, well, I would say standard dislocation creep, a little bit of motion at grain boundaries, but not so much. But in between, it's very interesting because the stress is still very high. So it's not really ductile, but still there is some ductility, still there is some plastic deformation, 10% here. And even as a CM, we already see a lot of motions at grain boundaries with grains which are popping up or popping down. The TM, the microstructure, is extremely strange. We see huge displacement at the grain boundary, evidence of ductile deformation at the grain boundary. But what is more interesting is the formation of olivine glass at some grain boundary. Here it's massive. Most often it's much less. It can be just a thin layer of a few nanometers, but still we have this formation of amorphous olivine at the grain boundaries. I will not spend a lot of time on that. It's described in the paper, but of course we checked carefully that that was not an artifact, that it has the composition of the olivine, exactly the same one. It's not partial melting, it's not incongruent melting. We checked also that in the starting material, there was no amorphous layer, that the grain boundaries were very clean, and so on and so on. So for us, it was really an evidence that due to the high stress level, there was the formation of this amorphous layer at the grain boundaries. We were a little bit concerned about the fact that, well, the Patterson press is at very low pressures. So what was the relevance of that for at least the lithospheric mantle? But so we asked Caroline Bollinger, since I mentioned that she showed microstructural evidence of grain boundary sliding, but in the multi-anvil apparatus at higher pressure, 3.5 GPa. So we decided to investigate her samples, and indeed we found massive evidence of amorphous layers at the grain boundary, with even here some clear evidence of shear lamellae demonstrating that those amorphous grain boundaries are the place where shear localizes. So at this stage, what do we learn? We learn that under high stress and even at 1000 degrees C, amorphization takes place at grain boundaries. Not only, I will show you, but mostly at grain boundaries in olivine, and that this is not inhibited by pressure. So for that, it gave us a few ideas, and especially we was wondering whether it could be playing a role at the lithosphere-asthenosphere boundary. It's complex. There are many ways to apprehend this feature, but I think that one important point is that it's very much linked to a temperature, to an isotherm. And you know, on the one hand, you have this temperature control, on the other hand, you have glass. And we know that the rheology of amorphous material is strongly dependent on temperature, much more than crystalline material, because there is a given temperature, the glass transition temperature, where there is a huge change in rheology, you know, with the viscosity, which is dropping by many orders of magnitude. So this is really something which was ringing a bell. This is something which is known for many amorphous silicates, anorthite dioxide. You see here the big drop in viscosity. But for amorphous olivine, that was not known because it's very difficult to produce it and to study it. So the idea that we proposed was that, well, at the base of the lithosphere, because of high stress, we could have this amorphization, and it's only when temperature reaches the glass transition temperature of amorphous olivine that then it would trigger plastic deformation and this drop of viscosity. Okay, we were not the first to observe the amorphization in olivine, not speaking about shock experiments, which is different. Approximately at the same time in the group of Phil Skimmer, by compressing micropillars of single crystal olivine, they did observe the formation of amorphous shear lamellae intracrystalline in that case. We did also observe a few intracrystalline amorphous lamellae in our specimens. This is one here that you can see in the middle, and I'm showing this picture to show also that there is no real relationship in between the dislocations of the ductile part of the story and the amorphous lamellae. It's not by accumulation of dislocation, for instance, that you produce this amorphous material. Usually they are not crystallographically controlled, except when they are close to the 0-1-0 plane. Here you see that in that case, apparently the lamellae like to align along this direction. Otherwise, it's not the case. We checked also in those very thin lamellae that it was the same composition, that it was amorphous olivine. We checked that by energy electron loss spectroscopy here. So we are on the same page. Interestingly, this is something that we saw everywhere here. It's an intragranular amorphous lamellae, but also at grain boundaries. Very often we see a few tiny crystals inside the amorphous layer. At that stage, it was difficult to know whether that was some remnants from the crystal, so incomplete amorphization, or whether because it's at 1000 degrees C, it was a nucleation, a recrystallization, if you like. Okay, we'll speak about that later. We decided to investigate in detail one intragranular lamella, which was going into a grain and stopping in the grain in the middle, because we thought that because of that we could have some clues about the formation mechanism, since we had the propagation which was stopped at some point. This one was starting on a grain boundary. Already here, from the shift of the lattice fringes, we have indication that shear is associated with this lamella. This work has been done for one part by Herman Béchet, who is here. So this is the teamwork that he did. Here, the lamella is inclined, so the contrast is not very strong. But you see that it nucleated from this amorphized grain boundary, going into the grain, and you see that there is an offset here. Again, we have many evidence of this shear. We have even more because not only we have this displacement here, but we performed FFT to have diffractions on both sides of the lamella, and from the change of intensity of the spots and from the rotation of the spots, we see that the shear is complex. Speaking in terms of fracture mechanics, that would be a combination of mode 1, mode 2, and mode 3. So it's very complex, not very much constrained by crystallography because it's amorphous. We decided, as I said, to investigate in great detail what was going on at the tip of the lamella. So here, this is a high-resolution ABF stem image. Very difficult to see anything, but to reveal the details of the strains, we use a geometrical phase analysis. So here, for instance, on the amplitude map, it's more easy to see the tip of the band, which is black because there is no amplitude where it's amorphous. And we see that at the tip, it has this shape, which with zigzags like this, which is very typical. But most interestingly, when we see ahead of the tip, we see those tiny contrasts here, which are very characteristic of the strain field of dislocations. We see also a rotation across the path of those dislocations. And well, since this contrast comes from the lattice planes, we can also identify the dislocation. They were C dislocations. And from the orientation of the Burgers vector, we can tell that those dislocations were not emitted by the tip and gliding to this position. It's not possible. The glide plane is oriented differently. So in fact, those dislocations were obviously nucleated ahead of the tip, ex nihilo, in the stress field of the amorphous, of the propagating amorphous lamellae. So this is the idea that we have about this process. You know, this lamella is progressing like that, is moving to the right. Ahead of the tip, there is a lot of stress, very high stress, high enough that dislocations are nucleated ex nihilo. And then, you know, you have a feedback. The stress field of the dislocation guides the propagation of the lamella, which follows the path of the dislocation. And this is probably the reason of this zigzag that we see. Okay, so this is what we inferred from the experiments performed by Sylvie de Mouchy. We wanted to reproduce that in the TM, and we did that with my friend and colleague Austin Idrissi in Belgium at the Université Catholique de Louvain, where we can perform in situ deformation in the TM. So this is the kind of sample holder that we use. It's from Heisitron, now Bruker. And in the small place where usually we have a sample, we have now a deformation device. The name is the push-to-pull. It's made of silicon. It's a MEMS. You have those 4 springs which are here, and there is a nano indenter. So when it pushes here on this place, this piece goes to the right. This one doesn't move. So here, where we glue the sample is pulled. It's under tension. So we can perform tensile experiments in this device. So this is the kind of small sample that we are using. As a scale mark, you have here a red blood cell. It's smaller than a red blood cell, bigger than a coronavirus. So this is approximately the dimensions which allow us to really isolate a single grain boundary and see what is the behavior of this grain boundary. What I would like to emphasize is that with this device, we can do quantitative deformation. That is, because we know the load that is applied, and since we can cut afterwards the specimen and measure the cross-sectional area, we have the stress. And since we are in the microscope, we see the sample, we take pictures of the sample, we can measure the sample, all the dimensions, so we have the strain. So we can get all the stress strain curves as I will show. So this is how we proceed. We prepare a foil which is larger. We perform orientation mapping like EBSD, but in the TM, which allows us to select the grain boundary that we want, and then we prepare the small tensile specimen that we want to study. So here you have the experiment which is running. You can see that you don't see anything, which means that there is no dislocations, nothing goes into the grain. We are still pulling on the specimen. At the end, you may see a tiny offset here, very, very small, nothing on the left, but here it moves a little bit and then bangs, it breaks. So it's not much, but still we can see that we did 2 cycles, one elastic going back, reversible, and then another one leaving the elastic regime and going into a plastic regime. And since we are in the TM, we can measure everything, the orientations of the grain boundary in every dimension. And doing that, we can transform the engineering stress in resolved shear stress. So for the first time, we could have like that the really individual stress strain curve of one defect of a grain boundary experiencing this grain boundary sliding. So we have the resolved shear stress as a function of the plastic shear displacement of this single grain boundary that we are studying here. Then, of course, we want to do some characterization. So we look at the fracture after the sliding, and indeed we see that we have amorphization. The grain boundaries which was gliding a bit was amorphized, and it's interesting to see that in this amorphous or amorphized grain boundary, we do see some tiny crystals, some tiny crystallites, which were remaining. And here it really reminds what I was mentioning before. So what we did observe that in the gas kettle samples, we had this observation of tiny crystals. So now I think that it's an indication that it's not something which recrystallized afterwards, but that was some remnants of incomplete amorphization. We did also a lot of FFTs on this amorphous olivine here at the grain boundary. And we see that we don't have circles, we have ellipse, which means that there is a lot of strain. It's heterogeneous and the strains are very high. It's in the range of 5 to here 13%, which is quite large. I will come back on that because it tells something about the stress locally responsible for amorphization. We wanted to do another kind of measurement. So this is another experiment. We did several. So here it's a 60-degree misorientation. I don't describe that very much. After fracture, we see again a small offset, which indicates that there was some sliding. But in this experiment, we wanted to use another technique, which is strain mapping using digital image correlation. This is a standard technique, but which was not used at this scale of the TEM before. So for that, we deposited a speckle of very fine, very tiny platinum particles, 3 to 5 nanometers. And from that, we could have the strain maps first here in the reference frame of the specimen XY, but then of course we want to do more. So again, we measured all the orientations in all directions of the grain boundary to calculate the shear strain along the grain boundary, which is more relevant for this study. What you can see here that for most of the study, we don't see anything. It's only very, very close to fracture at the end when we enter the ductile regime that we do see the localization of shear along the grain boundary. So another evidence of the grain boundary sliding. So to understand a little bit the origin of this mechanism, we did calculate the ultimate properties of olivine. What is the ideal strength? The ideal strength is a deformation that you can reach without any defect. And this is something that Karine Gourier here in Lille did calculate using first principle calculation. This is done at the scale of the unit cell, and by performing either tensile or shear test as we like. So these are the kind of curve that you can have, and the maximum stress gives the limit of stability, of mechanical stability of the structure, depending on which direction shear is applied. You see that the strains, I'm speaking in terms of strains to compare with the measurements, are here, like a lot of them are 18%. In tension, it's smaller, and we find values which are of the same order of magnitude as stress which was frozen in the amorphized grain boundary that we had. And interestingly, the softest direction here, 010, remember, it's the one that we did observe in the TM. So we have here, I think, consistent evidence that this is what is occurring. So our idea that amorphization here is really directly triggered by very high stress, which locally destabilize the olivine structure. Of course, well, we did this work on olivine, but this is a phenomenon which was already observed in other materials, and of course, ceramics, tough materials. So here, for instance, boron carbide, where they did observe experimentally, I think it's in nanoindentation, some grain boundary amorphization, but also something that they did calculate by molecular dynamics. That was observed before in boron carbide, but during shock. But I think that it's probably kind of equivalent. They have these lamellae, and with some evidence, as you can see here, of shear across the lamellae. This is boron carbide. Same thing in silicon carbide during shock, and also here they reported evidence of shear along those amorphized grain boundaries. So looking back at the literature, we think that there is a large body of consistent evidence that this kind of shear amorphization, of stress-induced amorphization, not only exists, but also can act as a deformation mechanism. And this is something that we wanted to emphasize in this paper that we wrote in 2022. So coming back to this Christmas tree, for instance, from the beginning, or maybe on these classical deformation mechanisms maps, from HB, which try to summarize all deformation mechanism, we think that something is lacking, probably here, where usually people consider only low temperature plasticity. There is probably here a small domain where this stress-induced amorphization can play a role, and this is something that should be, we think, that should be considered. But then it changes a little bit the perspective, because since now we have this amorphous layer at the grain boundary, now the rheology of the polycrystal depends also very, very much on the rheology of amorphous olivine, and this is something that was not new, and we decided to give some attention to this problem. The problem is that amorphous olivine is not easy to produce, so it's possible here. I should stop that noise here. It's possible here to do that by pulsed laser deposition. This is done in Ruhr-Universität Bochum by Ralph Domen. The problem of this deposition process is that it makes thin films, which are not easy to use for mechanical test, except if we use nanomechanical testing. And this is what I want to show you now. The simplest test that can be done is nanoindentation, and that was done by Paul Barral when he was in UC Louvain. He's now in Saint-Étienne. Usually, just by making some prints like that, you can have the hardness. But Paul was doing something more sophisticated by maintaining a rig and by measuring continuously and maintaining constant the surface area of the indent, and hence the contact stiffness. He could follow the evolution of the stress. So this is a relaxation test. And by doing that during 1 hour, he could really extend the range of nanoindentation data to lower strain rates. Nanoindentation is quite fast. Usually it's 10 to -1, 10 to -2 maximum per second. By doing that, Paul could extend to 10 to the -7. So this is always something which is interesting for us. And also by having that, he could measure quite precisely the strain rate sensitivity, which is a very good indication of the mechanism. It's interesting here to compare the strain rate sensitivity of amorphous olivine and from crystalline olivine. And you see that there is different in slope. And if we extend a bit this range, we can see something which is interesting. So this is what we see here in the lab. And remember from the lab experiment that we had, we said, well, grand boundary sliding is important. You know, it plays an important role. But see what that would give in nature, in the lithosphere, because of those slopes. You know, the difference is much more large. So it means that if we see this mechanism very active in the lab at natural strain rates, it might be much more important. So this is something which is important to keep in mind. I would like to show you another nanomechanical test that maybe you are less familiar with, which is on-chip nanomechanical testing. And this is done by Michael Coulombier, also in UC Louvain. So this is Michael. As you can see from the way he's dressed, this is a technique which is using microelectronics technology. You see here a silicon wafer. Usually this is done to make transistors, chips, and so on. But if you zoom in here, what you will find is not transistors or electronic components, but deformation experiments. So this is a way to have on a silicon wafer many let me find back my pointer, many deformation experiments and to get a lot of information. So how does this work? This is the principle, quite simple. This is the silicon substrate. And first you deposit a material which will be the actuator. It's silicon nitride because it contains a lot of internal stresses. Then on top of that, you deposit your specimen. Here it's amorphous olivine. Of course, it's patterned like that so that the amorphous olivine has a nice dog bone shape. And you have here two pointers, two markers, which can follow the strain. Of course, nothing happened at that stage until you etch the substrate and even below the machine. And when you do that, you freeze the machine and then the actuator pulls on the sample. So this is what happens here. And then you have a final stage because you cannot follow that. This is too fast. It's impossible. What you measure is then the displacement at the end. And this is what gives you the information because since you know the mechanical behavior of the actuator, when you have the displacement here, you know the stress from the elasticity of the actuator. And you also have the strain in the specimen. So each machine will give you a point that is a couple of a stress and a strain. And to build up a stress strain curve, we need to have many machines with different dimensions, which will experience different stresses. So this is the kind of stress strain curve that we can have. And from that, we have many information on elasticity, fracture stress, and so on and so on. But there is something which is more interesting, and that was a development that was made during this study, is that, well, you do the measurements and then you leave the chips, but the actuator is still pulling on the specimen. And so it continues. So if you come a week later, a month later, 6 months later, 2 years later, we did that during 2 years, you see that the strain continues to evolve. We followed several machines like that, and it's interesting to see that even in the lowest part of the curve, that is at low stress, this does happen, meaning that it's viscoelastic behavior in that case. So we could plot here the engineering stress as a function of the plastic strain rate and calculate again the strain rate sensitivity. Interestingly, we find the same value as with nanoindentation, but look at that. Here we can extend the range down to 10 to the minus 12. I think that this is the world record. It's the slowest deformation experiments that we have ever obtained, and with a consistency in the mechanisms. We wanted also to understand better how this amorphous olivine deforms. So we have made also some calculations, and that was done during the PhD project of Valentin Delbecq, supervised by Philippe Carré, here in Lille. I'm not going to describe very much the details. This is classical molecular dynamics and molecular statics as well, using lamps. This is, we perform several kind of tests. This is what we call quasi-static, which is good to follow very precisely the different steps. And we see here that the plastic deformation is made of a lot of plastic events. So we can really isolate the plastic events and then make the analysis of what happens in the specimen. And basically, we see that there are some places where the atoms do not follow the regular shear strain, and they deviate from that. So there are places which localize plastic deformation, and these are what is called shear transformation zones. The shear transformation zone is a concept that Ali Argonne proposed in the late 70s to account for plastic deformation of amorphous material. And we do see that this is what happens in our specimen, and that in our amorphous olivine, it involves tens or a few thousands of atoms. This is the typical size of what we saw. We decided to use that to model the mechanical behavior. So if we analyze here, not only the STZ, but also the strain field around the shear event, we see that it has a typical quadrupolar symmetry, which is very typical of what would be produced by an Eshelby inclusion. That is an inclusion which becomes a spherical inclusion, which becomes an ellipsoid, which has some plastic deformation. So what we do is that we fit here an inclusion at the center of the plastic event. We adjust the strain so that we reproduce the far field of the strain, and then we have now a synthetic plastic event, but for which we know the elementary plastic strain. So since we do that for all the plastic events that did occur in the specimen, we can try to rebuild the stress strain curve, adding the elastic contribution and the contribution for all those plastic events. So when we do that, of course, first we reproduce quite well the elasticity. We reproduce the first major stress drop, and then afterwards we reproduce quite well all the stress strain curve, meaning that with this plastic event that we identified, we really understand what are the processes in the amorphous olivine when it deforms. So having understood that, we could make different tests at different temperatures and different strain rates. And then we have some data that we could fit with a modified Herschel-Buckley law. Herschel-Buckley is used to model the influence of strain rates usually, but Chatterjee et al. Proposed a modification to introduce the influence of temperature, and we saw that it works very well with only one set of parameters. We could describe all the curves. We, of course, wanted to address the influence of pressure, which is not huge, actually, which is interesting and, well, consistent with the observation that we made at the TEM. So we see that indeed the pressure here only affects the first coefficient of this flow law. So we have now a complete set of parameters. We can describe the influence of temperature, strain rate, and pressure of this glass. Does that compare well with the experiments? So we used the curve at 300K. We did a fit with a Apollo law to get the strain rate sensitivity to compare with what we obtained from the experimental. And that is absolutely fantastic because we see that we have exactly the same behavior, the same strain rate sensitivity across like 24 orders of magnitude. So what the mechanism that we characterize in details in molecular dynamics is the same as the one which is activated in nanoindentation and in the lab on chip experiment. So we are very confident that this is also what could happen in natural strain rates. So, and this mechanism is the shear transformation zone as proposed by Ali Argonne. So to conclude, what did we learn in this study? Well, we learned that olivine, if subjected to high enough stress, can become mechanically unstable, and one response is solid state amorphization. It affects, of course, first the weaker parts, which are the ground boundaries, but it can also affect the bulk of the crystals. We studied the rheology of amorphous olivine. We have flow laws which take into account pressure, temperature, strand rate. We know the mechanism which is associated with that, the shear transformation zone, and we demonstrated that this mechanism is valid across a very wide range of strand rate. And it's on this positive conclusion that I stop, and I thank you very much for your attention.
Thank you very much, Patrick, for a real tour de force webinar. Thank you so much. Very impressive work. The talk is now open for comments, questions, and discussion. Just unmute yourself, raise your hand, or put your question or comment in the chat.
Hi, great talk. I was wondering why there wouldn't be a 010 slip plane.
Excuse me, the
Going back to the early part of the talk, when you're talking about the crystallographic constraints on the system and all of
the
it.
010 slip direction. In fact, you know, very often when people describe that, they refer to the length of the unit cell of olivine, which is 1 nanometer, something like that. Actually, that is not the reason. That is not the reason, because, for instance, when we studied wozellite, which also has a quite long unit cell, we could have dislocation just by dissociating the dislocation. So in fact, this is something that we looked by atomic scale simulation. When you try to shear along this direction, what you do is that you push two oxygens one against the other. So in fact, in that case, you know, to force the oxygen to jump above the other, you need an energy which is too high. So in fact, those dislocations are very unlikely. We do observe a few sometimes, you know, but it's very inefficient because of that. So the real point is that two oxygen in this shear process are forced to go one against the other.
I see. Cool, thank you.
The plot you showed 3 slides back, it's very impressive, putting all of those phenomena on the same plot, 28 orders of magnitude from tectonic.
Yeah, this is really a surprise.
That's very impressive. And this lab on chip technology is just amazing. I was unaware of that. Has it been applied to many other systems in looking at going beyond the few systems you looked at here, you know, in terms of technology or technological materials?
Yes, it was mostly used to study metals before nickel, aluminum, thing like that. It's very versatile. We use that only for tensile and plasticity, but it can be used also to do, they call that the Kraken chip, to do fracture mechanics and so on. It's a very nice technique, but it's very delicate because in fact the specimen is part of the experiment. So you really have to fine tune and to change potentially the dimension of the actuator depending on your specimen, so that it fits. So it requires some kind of fine tuning, and also, and I think that this is the biggest limitation. This is limited to material that you can deposit, you know, which is not the case for everything. But we tried, since we deposit amorphous olivine, we tried to crystallize to heat up, you know, to crystallize, to have crystalline olivine And so this is something that is in progress. We are also trying to develop a high temperature version of that to be able to do tests at high temperature.
Has it been used on any scale in nano X-ray diffraction experiments?
Yes. Not with olivine. Well, at least there was one test which was not very consistent, but yes, this has been used. I think it's with nickel that they transported that. It's very easy to transport that to a synchrotron. So people did that. Yes.
Right. Okay. Sabri, go ahead.
Yes, I have just a quick question about what type of molecular dynamic simulation. Is it first principle? My guess it's really large system. And have you considered any machine learning training for molecular dynamic?
No, that was lumps, and with there is with for olivine there is the potential from pedone which give quite good results. So this is the one that we were using. So we didn't have to develop our own potential. So this is standard molecular dynamics and molecular statics using lumps.
Thank you.
Yeah, may I?
Yes, go ahead.
Yeah, Patrick, great talk. Thank you. And if I understand correctly, so I believe that your flow rule is sort of composite. So something comes from molecular dynamics, something comes from experiment, because I remember that in molecular dynamics, stress level is like 4 GPa, 4 GPa. But in experiment, it's probably 1 GPa, so it's like composite model. Is it correct?
No, the flow law is only from the result for molecular dynamics. Of course, as I said, we are very far in the upper right corner of the plot in terms of stress and strain rate. But what is surprising here is that we have the same kind of mechanisms. The stress levels, if we extrapolate the result from molecular dynamics, if we extrapolate at the same level of the experiments, there is a small offset. I did not show you that because it cannot be compared with those experiments, but it can be compared to some other experiments of push-to-pull that we did, but I didn't have time to show that. There is a small offset, and I think that the reason is interatomic potential, which is a little bit too weak. So I think that it should be it could be very easily rescaled so that we have a really continuous description across the scale. This is not something that we did yet. We were first more interested into the mechanisms.
Okay. And another question, this mechanism that you observe that at the tip of
Yes.
amorphous band, there is nucleation of dislocation, and then band follows this dislocation path. This is similar to ductile fracture, but instead of dislocation, there are there are voids ahead of crack tip, right?
Exactly. Yes.
Exactly.
Yes.
Yeah.
Yes. It's something which is not completely localized. There is some damage ahead, and it's following the damage. Here, the damage are dislocations. In the case that you mentioned, it can be voids, but it's exactly the same kind of mechanism. Yes, sure.
Okay. Thank you.
Welcome.
But coming back to the geologic implications of amorphization of olivine, what can you say about the kinetic stability of the amorphous lamella? Have any annealing experiments been done to look at how stable they are over periods of time and to recrystallize? Anything like that done experimentally?
It's in progress. We did we did some annealing experiments on the amorphous olivine deposited by the PLD. So we see that crystallization occurs, not surprisingly, around the glass transition temperature that is around 900 degrees C, something like that. We do see that the nucleation comes earlier. We still what is in progress is that we want to do the same kind of experiments on really the glass which results from the amorphization, because maybe it's the same, maybe not, So this is something which is in progress. We bought a high temperature stage for the TEM, and we are preparing that. But we know that amorphous olivine is very unstable, so I don't think that it would survive very, very much. What I would like to look is what is the morphology after it crystallizes. Do we completely heal with no indication that at some point it was amorphous, or do we have, I don't know, like tiny crystals, something like that, which could be something that we could look in natural specimens to see whether this did occur. There is no hope to find in natural samples evidence of this process remaining, except if the way it crystallizes leaves some indication, maybe. I think that when it's like 2 nanometers, there's no chance, maybe for the others. So this is an experiment which is planned.
Yeah, good. Yeah, some fossil imprint of the lamella.
Quite unlikely, but it's worth looking at.
Yeah. And what's known about the local and more importantly, the medium range structure in amorphous olivine or forsterite? Can you say anything about that?
No, nothing. No.
Hasn't been
I think that it would be mostly with ramen that we should be seen with the MD. It's not what is the most easy to do. We did some nano diffraction to try to see something, not big success. So I think that with what we can do, no indication. I get that probably it's with Raman spectroscopy that more indication could be obtained, I guess.
I'm thinking of a paired distribution function analysis with neutrons or X-rays, for example, to look at the longer range order disorder. That has
we did that from electron diffraction. Maybe we are not good enough to analyze that. The first peaks are very clear. After that, it's very confused. I don't know. Maybe it's worth being explored more into detail.
Right. More questions, comments? Barbara, go ahead.
Hi, thank you for the great talk and great science. I think you said it, but I missed it, about the starting material and composition. Is it all pure forsterite, or is there olivine actually? So is there iron in any of the samples?
So the specimens deformed by Sylvie Demouchy was pure forsterite. The amorphous olivine, which was deposited by PLD, there is a little bit of iron, like 10%, something like that. In this range, we see not much changes. I can tell you something, but I did not present because these are preliminary results. We tried also to do nanomechanical testing. Not only with this composition, as I said, like 10% of iron, but we did that also with some specimen containing 20% of iron and 50% of iron. And
so I would expect that to...
Excuse me?
I would expect that to have a significant effect.
Indeed, with 50% of iron, no amorphization. Completely brittle. With 25%, we find at the TM a tiny layer of amorphous material, so there is a little bit, not so much. So indeed, we have an evolution. So when we increase the iron content, the response to mechanical instability is fracture, not amorphization.
And would you expect the way natural crystals versus synthetic and all these different types, that the starting defects that all these materials have could have a strong impact on?
Besides iron?
Yes.
Besides iron, no, I don't know exactly what you have in mind. Of course, amorphization will, of course, always start at weakest places,
Yes.
so if you have some defects somehow, but in olivine, what could it be? We don't see that dislocation, for instance, play any role. We don't see that it starts from dislocation or whatever. So besides grain boundaries and besides the iron content, I don't have. Do you have something in mind?
Not specifically, like my literature is not fresh enough. And finally, was some report of natural amorphous olivine from from meteorites or shock?
Yes,
shock?
before that, the amorphous olivine was reported from shock. I don't know, from experiments, and that dates back to the 70s. So
yes, that is recovered by nature for a long time. Okay, and can you compare the TM atomic structure?
I did not study those amorphous olivine coming from shock, but yeah, that would be interesting to compare indeed, and especially following the suggestion of Ross, trying to infer more about the medium range structure and things like that. Sure, or maybe the thermal stability. We know that there is polymorphism, so.
Oh, it's a sort of infinite kind of scenarios. One has to start somewhere. Yeah, thank you.
You might check with Raymond Jeanlot, because he studied amorphous olivine as part of his PhD thesis.
I know, yeah. He was the first to show the occurrence of amorphization in olivine. Yeah.
I think Tom Sharp also has some data on natural material.
Ah, really? This I did not remember, but I check.
My recollection.
Okay.
Thank you. More questions, comments? If not, thank you, Patrick, for a terrific talk.
Thanks to you.
And we look forward to engaging with you further and maybe another talk down the road. Thank you so much, and have a good evening.
Thank you very much. Bye-bye.